Hello everyone, welcome to MRU E-Learning, powered by Malla Reddy University. Myself, T. Rajan Kumar, Assistant Professor, Department of CSE, School of Engineering. Now, my concept is RAFT Consensus Protocol for blockchain, achieving fault tolerance in distributed system. So here in this, you can see two terminologies. One is RAFT Consensus, another one is blockchain. Here these two are correlated with each other and achieving fault tolerance in distributed system. Let's see in detail about the concept. First, we'll see about the blockchain. What is a blockchain? Okay. So now, blockchain can be defined as decentralized computing and information sharing platform that enables multiple authoritative domains such as don't trust each other and cooperate with each other and coordinate in terms of work and information and collaborate in rational decision making. So here blockchain is nothing but decentralized computing and information sharing platform. That is a blockchain. Next, we'll see how it works. How does blockchain works? Imagine we'll take an example for this. Suppose you and your friends have a copy of some data and that is nothing but maintained in notebook. And every time someone wants to add a new entry, like a transaction, they write it on and in the notebook. So, but before it's officially added, everyone else check with it, whether it is correct or not. If it is correct, once everyone agrees, the entry is added to all the notebooks. So this process ensures that the information is accurate and can't be tampered. So in this example, you can see the consensus also, RAFT Consensus Mechanism. Okay, we'll see in detail about that also. This is how the blockchain works. Next, here some technical terminologies. Blockchain operates as follows. First one is blocks and chains. Second one is decentralization. Third one is consensus mechanism. And fourth one is immutability. Now, first one we'll see about what is blocks and chains. Here, data, that is nothing but a transaction, is stored in the blocks. And each block contains number of transactions and a unique code, nothing but hash. That hash unique code is linked to the previous nodes, nothing but blocks. So that forms a chain. Okay, blocks and chains. Next one, decentralization. Okay, instead of storing in a single place, nothing but bank servers. Here, blockchain is a distributed. So each block will have stores multiple blocks. That is decentralization. Next one is consensus mechanism. Consensus mechanism, nothing but before a block is added. Before a block is added. So here in the network of computers, network of nodes, everyone must agree so that that block is added. That is the process of consensus. Next, immutability. Here, after adding the block into the network, it can't be tampered or altered. If you want to add or alteration or doing some changes, there must be an agreement between the networks. So that is the power of blockchain. So the blockchain maintains safety and immutability. Next, here before blockchain, we have a concept creating a document offline and share it in mail. You can see this diagram. Whereas era of shared documents, simultaneous working. Next one, challenges of centralized system. What are the challenges? Drawbacks. Single point of failure. One is prone to single cyber attacks. Second one is loss of data if server crashes. Third one is insufficient load balancing. Fourth one is governance under single protocol. And fifth one is if administrator plays with logs and databases. So these are the challenges of centralized system. So cyber attacks maybe happen and server crashes maybe happen and insufficient load balancing. Third, and governance under single control and administrators can play about the logs and databases. Now, coming to the why blockchain we need. So here, internet database for decentralization. So each node maintains a local copy of global sheet. Second one, internet makes care of consistency. And third one is identical copy of information at minimum fractions. And next one, here you can see in this diagram, it's a block and consists of transactions and a hash address linked to the next block. Like this, it's a block. So here, it's a distributed ledger of all the information. And second one, history of information with track of changes and historical information utilized to add new information. Next one, characteristics of blockchain. So you can see here 6 characteristics which plays a major role for the blockchain. First one is protocols for commitment. Second one is consensus. And third one is security. Fourth one is privacy and authenticity. And fifth one is auditability. And sixth one is provenance. Let's see one. Protocols for commitment. Here, valid transactions registered in definite time. Second one is consensus. So we are discussing about that only, RAFT consensus. So consensus is nothing but ensures consistency and updation. And third one is, you can see security, ensure tamper-proof system. So no other person wants to alter to the block. Here maintains the security. There must be an agreement. That agreement is nothing but 51 majority of the computer networks people must be agree. Then only it can be changed or altered. That is the security it is maintained. So ensure tamper-proof system. Next one is privacy and authenticity. So here user access controls and role-based access. And the next one is auditability. So logging of actions. Each and every logging of actions are maintained. Okay. Next one, provenance. Actions taken over blocks and tracked from origin. Next, we'll see about blockchain components. So first one we can see is a network. In this network, you can see node A, node B, node A, node B, and node C. So here Ethereum, you are seeing this is Ethereum. Ethereum is public, permissionless blockchain platform. Okay, here in this you can see transactions and smart contracts. Smart contract is also one of the component for the blockchain. And the transactions are recorded in the blocks and maintained a copy in each and every nodes, like node B, node C. Every transactions are recorded in each and every nodes. So that is the network. Next one, smart contract. Smart contract is nothing but there is no middleman in this. Okay, only one-to-one can be exchanged. Nothing but you can see concept first realized in 1994, and smart contracts helps in exchange of money, property, shares or anything of value in a transparent, conflict-free way while avoiding the services of a middleman. You can see here, smart contracts helps in exchange of money, property, shares, anything of value in a transparent and conflict-free way while avoiding the service of middleman. Okay. Next, third one, self-executing contracts, blockchain contracts or digital contracts. These are the terminologies of the smart contracts. Next one, contracts can be converted into the computer codes also. Nothing but hash, like SHA codes. We have different kind of codes that can be converted. Contracts can be converted like encryption, decryption way. Stored and replicated on the system. Stored and replicated onto the system. Okay. Next one, fifth one is supervised by the network of computers that run the blockchain. So this is about smart contract. Next we'll see about the third one is blocks. This is another component for the blockchain. You can see is blocks in this diagram, block 10, block 11, block 12. In this block you can see transactions, number of transactions and timestamp, okay, and hash function, okay, and nonce. These are the 4 things are stored in the block, and each and every block having an hash address. It is linked to the next block. It is linked to the next block. It is linked to the next block. Like you can see here, hash 01, hash 02, like this hash 23, like this number of hash functions are stored for each and every transactions, You can see here, ledger is the collection of all the transaction. And second one is appends only with immutable paths, as it stores hash of previous block and distributed and replicated across. And fourth one, component consensus. This is our motto, consensus. Okay, what is that? Here you can see proof of work, proof of stake, and proof of reputation. First one, we can see proof of work. Those who owns more computing power governs the network. Okay. Next one, proof of stake. Those who have more money governs the network. This is proof of stake. Whereas proof of reputation, those who own deeper reputation and greater long-term audience base governs the network. This is about the three: proof of work, proof of stake, and proof of reputation. And you can see these are the decentralized control of information and share control tolerating distribution, validation of transactions, stopping malicious attacks, acceptance of terms of contracts. Next, 4 elements characterize blockchain. First one, replicated ledger, cryptography, consensus, and business logic. You can see in this first one, replicated ledger. History of all transactions, append only with immutable past, and distributed and replicated. Second one, cryptography. Integrity of ledger, authenticity of transaction, privacy of transaction, and identity of participants. Next, consensus. Decentralized protocol. This is nothing but decentralized protocol. And shared control tolerating disruption and transaction validated. Fourth one, business logic. Logic embedded in the ledger, executed together with transactions, and simple coins to self-informing smart contracts. So these are the 4 elements characterize blockchain. One is replicated ledger, cryptography, consensus, and business logic. Now we'll see about blockchain platforms. There are 2 types of platforms. One is public, another one is private. Public can be called as permissionless, whereas private can be called as permissioned. Okay. As you see in this public, you can see Bitcoin and Ethereum. These are the 2 public networks, Bitcoin and Ethereum. Whereas the private, we can see Hyperledger Fabric, Corda, Multichain, Quorum, and Ripple. Okay, these are the private. Okay, next we'll see about what is a RAFT, how it is correlated with blockchain. Okay, so what is a RAFT? RAFT is nothing but replicated and fault tolerance, achieving fault tolerance in distributed system. That is about the RAFT. So let's see, distributed consensus algorithm designed for simplicity and clarity. Next one, created by the persons Diego Ongaro and John Ostrott, and ensures all nodes agree on a single consistent state. Ensures all nodes must be agreed. That is that. Next, handles node failures and network partitions. Okay, it handles node failures and network partitions. Next, why RAFT for blockchain? So, understandable and easier to implement than Paxos. Here, this is a Paxos is a previous version of RAFT. So, RAFT is more understandable and easier for the blockchains. Next one, crash fault tolerance for trusted environments. Third one is fast block times, sub-second average. And the fourth one is efficient ladder election and log replication. Here, these are the 2 important terms, ladder election and log replication for the RAFT algorithm. So here, ladder election will be happened in the RAFT network and log replication will be maintained by the leader. Okay, we'll see about that also in detail. We have a visualization for the RAFT. So next, 3 core components. First one is ladder election, second one is log replication, and third one is safety. First one, leader election. One node elected as a leader to manage log entries. Next one is log replication. Log entries synchronized across all nodes. And safety, Committed entries never lost or rewritten. Now, node states in RAFT. Nothing but a node is nothing but a network, computer network node. Or you can call it as a system, server. So having a states. First one is follower, second one is a candidate, third one is a leader. So here, these are the three states in RAFT protocol. First one we'll see what is a follower. Follower receives commands from leader and replicates log entries. Candidate. Candidate is nothing but node requesting vote to become leader. Leader is nothing but append entries, send heartbeats to maintain authenticity or authority. So let's see leader election mechanism. So each node starts as a follower. So each and every node will start as a follower with random timestamps. Okay. If no heartbeat received, timed out, we can call it as timed out, followers will become the candidate. Followers now what happens will become the candidate. Now candidate requests votes from other nodes. Next, first candidate to receive majority of votes becomes the leader. That is the leader election mechanism. Okay. Next, second one is how log replication will work. So log replication here, only leader can append entries to the distributed log. Nothing but here an entry is added to all other nodes. That is nothing but log replication. Okay. Next, leader sends log entries to all the followers, and followers acknowledge receipt and applies entries, and majority agreement ensures consistency and safety. So majority of the people, nothing but network nodes are agrees and ensures consistency and safety. Next we will see about the RAFT visualization. Here we have that. Now here RAFT visualization. Let's see. Understandable distributed consciousness. So what is distributed consciousness? Let's start with an example. So let's say we have a single node system. And for this example, you can think our node as a database server that stores a single value, that is X. Okay. Now, so we have a client also. Then send a value to the server. So here we are sending 8 value to the server. Okay. Now, coming to agreement or consensus on that value is easy with one node. When coming to the multiple nodes, let's see. So here multiple nodes, how we do comes consciousness. So that's the problem of distributed consciousness. So here, so RAFT is a protocol for implementing distributed consciousness. So let's look at a high level overview how it works. So a node can be in one of 3 states. I said you, one of 3 states. One is follower state, second one is candidate, and the third one is leader. So let's start. So the follower state will be represented like this. The candidate's state is represented like dotted representation. And the leader is represented in the bold manner. Okay. So these are the 3 states. So all our nodes starts in the follower state. Okay. All are in the follower states. You can see here, all are in the follower states. There are no candidates and there are no leaders also. Okay. Now, so if followers don't hear from a leader, then it become a candidate. Okay. So here you can see this is the candidate. Okay. So the candidate then requests votes from other nodes. Okay. So here you see in this visualization. So nodes will reply with their votes. So the candidate becomes the leader now. You can see in this diagram. The candidate is now becomes the leader because the response we got from the followers. So that a candidate becomes the leader if he gets votes from the majority of nodes. So this process is called leader election. Next, all changes to the system now goes to the leader only. Now, a client, it changes to the system now go through the leader. A client has been sent to 5. Okay, set has been 5. So each change is added as an entry in the nodes log. So the log entry is currently uncommitted. So it won't update the nodes value. When it will update, it will send the entry to all other nodes. The commit the entry, the node first replicates to its followers. So then the leader will wait for the majority of votes, okay, have written the entry. Now the entry is now committed on the leader's node. On the leader's node, you can see now. You can see 5 is committed and node state is 5 now. Now the leader then notifies the followers also that entry is committed. You can see the entry is committed. So the followers also got the information that entry is committed 5 and 5. Now, so the cluster has now become the consciousness about the system state. So this process is called log replication. Now we'll see about the leader election. So you can see here 3 nodes, node A, node B and node C, and term is 0 for everything, 0, 0, 0. Okay. So in RAFT, there are 2 timeouts settings which controls elections. Okay. What are they? We'll see. 2 timeouts. So first is the election timeout. The election timeout is the amount of time a follower waits until becomes a candidate. Until becomes a candidate. So the election timeout is randomized in between 150 milliseconds and 300 milliseconds. These are the timers. Okay. Now you can see in this visualization, node A, node B and node C has been started, and whether it is receiving any heartbeats. Okay. Now you see after the election timeout, the followers becomes a candidate. One of the follower. Okay. One of the follower becomes a candidate and starts a new election term. You can see here, node A has become the candidate. Why? Because it has been timed out. Whereas node B and node C in this, they are not in the timed outs. So these are in the follower states only. Now node A is a candidate and term is what? It is incremented to 1 and vote count is now 1. Let's see. Vote for itself. Okay. It had been vote for itself. That is nothing but 1. Okay. Next. So and sends out vote requests messages to the followers, nothing but other nodes. So you see here, it has been sent and the now term is what? 1. Voted for what? Voted for A. Here it has been voted for what? A. Next one you can see node C. Term is 1 and voted for what? A. So now again it is responding to the node A. If the receiving node has not voted yet in this term, then it vote for the candidate. And next. And the node resets its election timeout. Okay. Now you see, once a candidate has a majority of nodes, it becomes leader. You can see here, node B and node C has been voted for node A. So majority of votes has been received. So now node A has been the leader. Okay. So the leader begins sending an updated entries, nothing but append entries, messages to its followers. So these messages are sent in intervals specific by heartbeats, timed out. So followers then responds to each append entries messages. You can see in this diagram. So the election term will continue until a follower stops receiving heartbeats. Followers stops receiving the heartbeats and becomes the candidate. You can see next. You can see the node B and node C. Let's stop. We will stop and rewatch. We are stopping what? Node A. We are stopped. We are saying node B and node C. Whether election, which one is first? Election timeout. Now node B has been candidate, then it has been comes into the leader state. Now node B is now leader of term 2. So requiring a majority of votes guarantees that only one leader can be elected per term. So if 2 nodes becomes candidates at the same time, then a split vote can occur. split vote can be occur. Let's took that also. Let's took that, okay? You can see node A, node B, node C and node D. What is the term? 3 and 3, okay? Now, two nodes both starts an election for the same term. You can see here, node A term 3, node B term 4, node C term 3 and node D term 4. You can see node A and node C are having the same term, 3 and 3. And node B and node D are having the term 4 and 4. Okay, they are requesting votes, vote count. Okay. So, and reaches a single followers node before the other. Now, you can see each candidate has 2 votes and can receive no more for its term. You can see node B and node D has becomes the candidate. Okay. Vote count has been 2 and vote count is now 2. Okay. Now, the node will wait for a new election and try again. You can see. Now, you see node B receives a majority of votes in term 5. So, it becomes leader. So, now this is about the leader election. We have seen about the leader election, how it has happened. Now, we will see about the log replication. How the log replication. Log replication is nothing but appending entries to all other nodes, nothing but follower nodes. And that has to be accepted. Okay, let's see that. Once we have a leader elected, we need to replicate all changes to our system through that node only. Now, you see, node A, node B and node C. Node A is not leader. B and C are the followers. What is the term? 1, 1, 1. And leader is what? A. And leader is what? A. So, this is done by using the append entries messages that was used for heartbeats. So, let's walk through the process. So, first a client sends a change to the leader. Let's see. It will send set 5. The change is appended to the leader's log. This is the leader's log set 5. Next. Then the change is sent to the followers also onto the next heartbeat. Now you can see node B and node C has been received set 5 and entry is committed once a majority of followers acknowledge. Node B has to be acknowledged and node C has to be acknowledged to node A. So they will send a response to the client also. Node A will send a response to the client. Now let's send a command to increment. Now we are going to increment add 2 also, next one. Now our system value is now updated to 7. So RAFT can even stay consistent in face of network partitions also. Let's see that also. We are going to partition the network. So here you can see node A, B, C, D and E. Whereas node B is the leader and term is 1. Okay. And node A is the term 1 and leader is what? B. Okay. And leader is what? B for node E also. For node D also leader is what? B. And node C also leader is what? B. Like this. Okay. Let's add a partition. Now we are going to add a partition. A and B separate, C, D and E separate. Okay. Now you can see node B is sending requests to node A. Okay. Let's. Next, node C. In this node C, you can see term 2 is sending request to node D and node E. Parallel, you can see in the parallel partition, network partition, node B is a leader in this partition and node C is a leader in this partition. Okay. So it is sending the request vote to the other nodes in the network. So let's add another client also and try to update both leaders. We are going to update the both leaders. That's one client will try to send value of node B, that is nothing but 3. Okay. So set 3 has been sent to node A. So node B cannot replicate to a majority. So its log entries stay uncommitted because there is no majority of votes. Now we are going to see node C. So set 8 has been received to node D and node E. Okay. Next. So the success, because it can replicate due to majority. Majority we have from node D and node E. Okay. So it has been success. So it is entered. Node C has been entered as 8. Whereas in this partition, node B because there is no other nodes, only single node. There is no majority of voting. So it is not committed. Whereas in the upper partition, it is committed. Why? Because here node C is the leader. It has been set 8 and send the request to the node D and node E, and that has been acknowledged. 8 and 8 send back the acknowledge to the node C, that is nothing but leader, and that is successed, committed. Okay. So now heals the network. Now we are going to heal the network partition. You can see node C is the leader now. So set 8 has been sent to every other nodes. Now it has been committed because majority of votes has been received. Both node A and B will roll back their uncommitted entries and match the new log entries. So our log is now consistent across our cluster. So this is about the RAFT visualization. Now we'll go back to the presentation. Okay. Now, what is the RAFT versus alternatives? We have some other alternatives. First one, we have seen RAFT. RAFT is nothing but safety, consistent, fault tolerance, simple, fast, sub-second blocks, trusted environment. Whereas another one, PBFT, practical, Byzantine, fault tolerance. Whereas third one is POA, proof of authoritative. So these are the other protocols. Now, what are the real world applications? You can see banking, disaster recovery, real-time processing, and private blockchains. These are the real world applications. In the banking, you can see consistent account balances and transaction records, and disaster recovery, resilience against localized failures, and whereas third one, real-time processing, fast fund transfer and confirmations, and private blockchains like Enterprise, Consortium, Ethereum. Next, key advantages: easier to understand and implement correctly, and fault tolerance can be achieved with majority rule principle, and efficient debugging and maintenance, and better performance in stable, low latency networks also. You can see in the fourth point, better performance in stable and low latency networks. Important limitations. We have some limitations. Crash fault tolerance, only assume honest leader behavior. And the second one is cannot protect against Byzantine attacks. Third one is blocks not cryptographically signed. And fourth one is limited to trusted, permissioned environments. Okay, here you are seeing Byzantine attacks, nothing but in the distributed network. Okay, each and every node should actively participate. Okay, if any other nodes are become traitors, that leads to Byzantine attacks. That is one kind of a limitation. Now, used in production where databases, blockchains, and distributed systems. We can see here in the databases where Cockroach database, MongoDB, TIDB, Yugabyte database. Whereas in the blockchains, Quorum, Hyperledger, Fabric. These are the two are Quorum and Hyperledger Fabrics are which comes under private, not public. Okay. Next, distributed systems, etcd and console. Now coming to the conclusion, RAFT provides a clear implementation consensus protocol ideal for permissioned blockchains and distributed systems requiring fault tolerance in trusted environments. So best for enterprises, private and consortium blockchains. And last, I want to say RAFT strikes a between simplicity and correctness. Thank you.